In this video, we're going to discuss section 7.9, substitution versus elimination. And in this last subsection of section 7, we're going to discuss how one can determine whether or not the outcome of a reaction is going to produce a substitution product versus an elimination product. And of those products, are there any regiochemical or stereochemical outcomes that one needs to consider? So to predict the products of a reaction and which products are major and which are minor, we need to consider the following three characteristics or aspects. The first thing that we should do is determine the function of the reagent. So in all these reactions, we're starting from alkyl halides, but what we add to our mix, we need to determine whether or not that reagent is acting solely as a nucleophile, as a base, or can that reagent act as both a nucleophile and a base? The second aspect we need to consider is we look to the substrate, the original alkyl halide. And we want to analyze the substrate for the number of substituents around that alpha carbon. So we want to identify the substrate as being either a tertiary, secondary, primary, or potentially methyl halide. Once we know the nature of the reagent and we've analyzed the substrate, we should be at that point able to predict the mechanism via which that reaction should go by. Now, once we've identified the mechanism, we'll have a sense for what products we will obtain from that mechanistic reaction. And at that point, we also need to consider any regiochemical or stereochemical requirements that will be observed in our product distribution. Now, to determine the function of the reagent, it's helpful to return to this particular table where we've categorized nucleophiles and bases as being either very good or strong, or very weak or weak. And so this can be very helpful in assigning what the nature of that reagent will be. Will it be a nucleophile? Will it be a base? Or could it have duality? It could be both nucleophile and base. And so again, some of our best nucleophiles are these three. These are polarizable centers. So the sulfur and the iodine centers are polarizable species. So this adds to their efficiency as a nucleophile. And in terms of bases, we've looked at mostly the anions of second row elements. So the oxides, the hydrides, the amide ions, and the carbanions. These are all very strong bases. So using this chart or this table to help you categorize the nature of the reagent can be very helpful. So what we'll do over the next few slides is we're going to look at various reagents that can function as either only a base, only a nucleophile, or have this duality of nucleophile or base. And we'll look at how, when those reagents are present in a reaction mixture that contains a primary, secondary, or tertiary alkyl halide, what the predominant mechanism will be. So if we look at the base-only category, and there's only a single species that we're going to refer to in this course with respect to a compound that only acts as a base, and that's sodium hydride. So sodium hydride produces the hydride ion in solution. So recall, anything attached to a sodium is going to be ionic in character and dissociate into the sodium cation and respective anion. So the hydride ion only acts as a base due to its small size. Because the hydride is so small relative to other species, it is not a very good nucleophile. In fact, it's a really poor nucleophile. So when the hydride is used as a reagent, it will only function as a base. And as a result, when the hydride is added to a primary, secondary, or tertiary alkyl halide, the only outcome that we observe is the E2 product. Okay, so in all scenarios, the E2 product will be the major product of that reaction, and we won't observe any substitution products for those reactions. Now, when we look at a reagent that can either act as a strong base or a strong nucleophile, so it has that duality, now we see some preference for one mechanism over another. So for a primary system, primary alkyl halide, the major product will be the SN2 product. So recall that the primary alkyl halide, very little steric hindrance, and so the major product will be that nucleophilic attack onto the alpha carbon. We will observe some E2 product, so it will be considered a minor product in this reaction, but the major product will be the SN2. And also recall that if the alpha carbon of your original substrate, your alkyl halide, is a chirality center, that the major SN2 product will be an inversion of configuration. Now for a secondary alkyl halide, we see a switch, and that the E2 now is going to be the major product of that reaction with our strong base strong nucleophile category. The reason for that has to do with steric hindrance, that once we go from primary to secondary, by increasing the number of groups around the alpha carbon, we reduce the efficiency of the SN2 reaction, which gives rise to a favoring of the E2 product. And finally, for the tertiary alkyl halide, we see no SN2 reactivity. We've talked about that previously, that due to the steric hindrance associated with 3 groups around that alpha carbon, there's just no efficient access to the alpha carbon by a nucleophile. So the only mechanism that we'll observe is the E2 mechanism, and so we'll see alkene formation for that particular scenario at all times. Now there's one exception that I want to discuss before we move on, and that is if the substrate is primary and we use a bulky base, that is, if we use potassium tertiary butoxide, then the E2 process is favored in that particular scenario. And the reason being that potassium tertiary butoxide, the butoxide ion being bulky in nature, that nucleophilic attack is somewhat hindered because it itself is hindering its access to the alpha carbon. So in that particular scenario, we will see E2 process being the favored product of a primary alkyl halide with tertiary butoxide. Now for the category where we only have a reagent acting as a nucleophile, these species are your hydrosulfide ion, your alkyl sulfide ion, bromide, iodide. These species are weak bases, and so they're not going to carry out any type of elimination reactions. Their main purpose will only be for nucleophilic attack. And so for a primary alkyl halide, we'll solely see the SN2 reaction, because a primary alkyl halide, to generate a primary carbocation, very unlikely, very unstable. And so the SN2 product is all that we observe. For a secondary system, we may obtain a mixture because we know the secondary carbocation, being more stable, can actually form. So we're going to end up with a bit of a mixture between the SN2 and the SN1. And which will be the major minor will really depend on the choice of solvent. So if we use a polar aprotic solvent, a solvent that will not interact with the nucleophile, then we'll favor the SN2 process. However, if we use a polar protic solvent, then we'll favor the SN1 process. So for a secondary alkyl halide, solvent does play a key role on which product will be major and minor. Finally, for the tertiary system, we will not observe any SN2 reactivity. The mechanism of choice will be SN1 going through that tertiary carbocation center. We don't have any nucleophilic access to the alpha carbon of a tertiary system, and so we won't see any SN2, only SN1. The last category of reagent is the weak nucleophile, weak base category, which includes water and the alcohols. And as you can see from this figure, when the substrate is primary or secondary, these reactions are really impractical. And that's primarily because they're simply too slow. In addition, for the secondary system, we see that we generate 4 different products, both substitution and both elimination products. And so that's not a synthetically useful reaction. Now, the previous 2 videos have discussed in detail what happens when a tertiary alkyl halide is in the presence of water or alcohols, and we saw that we generate both the SN1 and E1 products. Now, the E1 process is favored when we run the reaction at higher temperatures. Otherwise, the SN1 is the favored product. And as we'll see in a few examples, there are other ways in which we can generate the elimination product from a tertiary alkyl halide by choosing a better base. So these figures are nicely summarized in this table. We have here the 4 different categories that we use to describe the reagent. We can have a strong base, weak nucleophile, strong base, strong nucleophile, weak base, strong nucleophile, and weak base, weak nucleophile. And we will look at, again, how the effect of the substrate has on the mechanism of choice. So we saw for strong base, weak nucleophile, this was just primarily the hydride that we saw E2 regardless of the type of alkyl halide that we started with. If we're looking at the category of strong base, strong nucleophile, we saw for the less sterically hindered alkyl halide, the primary system that SN2 was the major product with some E2 formed. We saw that switch as we went from primary to secondary, but now E2 was the favored mechanism over SN2. And again, steric hindrance plays a significant role in the switch between those 2 mechanisms. And finally, for the tertiary system, we see no substitution in the presence of a strong base, strong nucleophile. We only see the elimination reaction to form an alkene. Now, in the category where we only had a reagent acting as a nucleophile because it was too weak as a base, we saw primarily SN2 reactivity for the primary and secondary alkyl halides and SN1 reactivity for the tertiary. And then finally, as we saw in our last slide, or previous slide, that when our reagent is water or the alcohols, that is weak base, weak nucleophile, the reaction with primary and secondary alkyl halides are really inefficient and impractical, whereas for the tertiary system, we see a split between substitution and elimination products where substitution will be favored at ambient or room temperature, but if we raise the temperature of our reaction mixture, we can force the favored product to be the elimination product. So this table will be helpful when you're working through questions that provide you with a substrate that you'll have to identify as being primary, secondary, or tertiary, and then a reagent which you'll need to identify as to the relative strength of that reagent as a base or a nucleophile. So finally, in table 7.6, here are again some guidelines for determining the regiochemical and stereochemical outcome of substitution and elimination reactions. So they're summarized here nicely. So we saw for the SN2 reaction that the nucleophile basically attacks the alpha position. And so that's where the leaving group is connected. And there's only one regiochemical outcome for SN2. However, the stereochemical outcome, we see an inversion of configuration for the SN2 reaction. For the E2 reaction, we saw that the Zaitsev product is generally favored over the Hofmann. And that is true that the more highly substituted alkene will be your major product, but that's only if you're not using a sterically hindered base. And so a sterically hindered base like tertiary butoxide, and that's the only one that we'll use in this course, and it's normally written in this way, it's the potassium salt. This is the only base that will favor the Hofmann product over the Zaitsev. Now, with respect to the stereochemical outcome, the process is stereoselective because when applicable, a trans disubstituted alkene will be favored over a cis disubstituted alkene. This process is also stereospecific, and specifically when the beta position of the substrate has only one proton, the stereoisomeric alkene resulting from the anti-periplanar elimination will be obtained. Okay, so refer back to those slides to look at that particular discussion. Now, with respect to SN1, the nucleophile will attack the carbocation, and that is again where the leaving group was originally connected, unless there was a carbocation rearrangement. So that can occur primarily when we generate a secondary carbocation, and there is the opportunity for a hydride or methanide shift. Now, in terms of the stereochemical outcome, we normally observe pretty much a 50-50 mixture, but we tend to see a little bit more of the inversion of configuration product over the retention of configuration due to that intimate ion pair that we talked about. And finally, for the E1, the Zaitsev product is always favored over the Hofmann product. And this process is also stereoselective. And so if possible, a trans disubstituted alkene will be favored over a cis disubstituted alkene. So now we're going to look at a variety of examples where we get to apply the information that we've learned in this section. In this first example, we have a pseudohalide and we have sodium hydroxide. So the first thing to do is to identify the nature of the reagent and then also to analyze the substrate. So if we look at our reagent, sodium hydroxide, we know that the active species is the hydroxide ion. And it is a strong base. So it is a strong base. It's also a fairly good nucleophile. So it's going to fall in the strong base, strong nucleophile category. Now, if we look to our pseudohalide, and I refer to as pseudohalide because we have this tosylate group as opposed to a iodide or bromide, for example. And so we know this is a very good leaving group. This is one of our excellent or very good leaving groups. But what we want to focus on is the alpha carbon. And we see that to this carbon, there is only one other R group. And so therefore, we can categorize this as a primary alkyl halide or primary pseudohalide. So for a primary system, in the presence of a strong base, strong nucleophile, the major product will be the SN2 product. And so nucleophilic substitution will be favored. So we can draw a mechanism where the nucleophile will attack the alpha carbon and we have loss of the leaving group. So this is a concerted mechanism and the net result is the formation of an alcohol. And our leaving group is the tosylate. And so the major mechanism for this reaction is the SN2. Now there's no regiochemical aspects that we need to really concern ourselves with. We know that the nucleophile will attack the alpha carbon, and so that will give rise to this particular product. In terms of stereochemistry, we don't have a chiral center, and so we don't have to concern ourselves with whether or not we have inversion or retention configuration. But if it were a chiral center, recall that it is the inversional configuration that we observe for the SN2 reaction. In a second example, let's look at what happens when we use the same pseudohalide, but we change the reagent to tertiary butoxide. Now, the active species in tertiary butoxide will, of course, be the tertiary butoxide ion. And so what's different about tertiary butoxide versus the hydroxide is the bulky nature of it. This is a sterically hindered base. So although it is a strong base, it's not a great nucleophile due to the bulky aspects of it. So when presented with a primary alkyl halide, where we would expect an SN2 reaction, for this particular species, the elimination reaction will be favored. And so it is going to be a hydrogen at the beta position, and I'll explicitly show that here. It will be lost as a proton, and as a result, we will form the elimination product, as well as the leading group. And it's also good to show that you've formed protonation, the protonated base, which is tertiary butanol. So the net result is an elimination product, and so this is the E2 mechanism. So to summarize, in both cases, we're starting with a primary pseudohalide, but the nature of the reagent, even though they're both strong bases, we see SN2 for the hydroxide species, whereas we see E2 for the tertiary butoxide. Now, we said in the previous slides that this is an exception, but it is a useful reaction for converting primary alkyl halides or pseudohalides to alkenes. In this next example, we have a similar pseudohalide, except now instead of starting with a primary system, we have a secondary system. So for the secondary system, and using sodium hydroxide again as our reagent, it still is acting as either a strong base or strong nucleophile, but we'll observe some regiochemistry associated with this particular substrate. So we have now two possible beta positions. We have a beta position here and a beta position here. And so the preference will be to form a alkene that is most highly substituted. So for the hydroxide, which doesn't have any steric encumbrance, we're going to see the formation of a pi bond between this alpha and beta carbon as opposed to this alpha and beta carbon. So similarly, we have our active species is the hydroxide. I will draw in a hydrogen for our mechanistic purposes, and we can draw our curved arrows to represent the electron movement. And the net result is the formation of the following alkene. And as you can see, we're going to have potential stereoisomers generated in this reaction, with the trans isomer being the more stable of the two. So the trans will be the major product, cis will be the minor product. And of course, we should also include that we will generate a molecule of water, and the leading group will be erythrosylate. So the major mechanism will be the E2 mechanism. And we have a stereochemical outcome in which the trans 2-butene will be favored over the cis 2-butene. Now, if in this example we had used sodium methoxide or sodium ethoxide, we would obtain the same product outcomes. Now, if we were to use tertiary butoxide, though, in this particular example, we see some regiochemistry. Now, again, the tertiary butoxide, drawn in this way, our active species is the tertiary butoxide ion. Draw one proton for mechanistic purposes, and draw the curved arrows. And so in this particular instance, yes, it will still be E2, but our major product will be the following alkene. side products. So again, we have the E2 mechanism being the major mechanism resulting in the formation of this particular alkene, which is a constitutional isomer of the alkenyl structures, alkenyl compounds drawn here, but here we don't have any cis-trans isomerization because we have similar groups on this particular carbon. Nonetheless, it shows you that you do have control over the regiochemistry of your final alkene by choosing a particular base, whether it be the hydroxide, the methoxide, or ethoxide. They will all generate this particular mixture of alkenes, whereas a tertiary butoxide will give you the less highly substituted alkene. In this example, let's use the same pseudohalide, but let's change the nature of the reagent. So we still have a secondary pseudohalide, but now we have a species which doesn't act as a strong base, strong nucleophile, but only as a strong nucleophile. This species, the active ingredient, if you will, is the alkyl sulfide ion. So in this case, it's an ethyl sulfide ion. And so this, due to its larger size, the sulfur atom, we've seen that these are very polarizable species, and so very good nucleophiles as a result. Now, because we have a secondary pseudohalide, we would expect that both SN2 or the SN1 mechanism may occur. Now, to differentiate between what the major mechanism is for this particular example, we look to the solvent. And so you see here what's listed below the arrow, which is typically where we would place solvent conditions or temperature or timing, is the acronym or abbreviation for dimethyl sulfoxide. So dimethyl sulfoxide, you may recall, is a aprotic solvent. That is, it's a solvent that is unable to form hydrogen bonds with nucleophiles. So as a result, by it not interacting with the nucleophile, it's promoting the SN2 reaction. And so in this example, we will have nucleophilic attack onto the alpha carbon and loss of leaving group. And so that's going to generate a sulfide as shown. And we will also generate a leaving group. And that is basically it. So this is going to be our SN2 mechanism. And there may be some minor product associated with the SN1 mechanism, but the major product of this reaction will be this particular sulfide via the SN2. And again, the solvent plays a significant role in this particular example. In this example, we're going to start with a tertiary alkyl iodide, and the reagent is ethanol. And so I've just given away the first part. If we analyze the substrate, we see that there are 3 groups attached to the alpha carbon. So this is a tertiary system. And if we look at the nature of our reagent, we recognize this as an alcohol, ethanol, and alcohols are weak bases and weak nucleophiles. So it'll be that last category that we looked at previously. So we know that when we have a weak nucleophile, weak base, that reactivity with primary and secondary alkyl halides is really impractical. But for a tertiary system, we do see both substitution and elimination occurring. So they're competitive with one another. So at normal ambient room temperature, which is often not shown if that is the case, we would expect the SN1 mechanism to be the major mechanism for product formation. So in this example, if we were to draw our curved arrows, The first step in this reaction is the dissociation of this carbon-iodine bond. And so that gives us the following. And this is in equilibrium. We'll discuss more about equilibria in later examples, but we know that this bond dissociation event is slow, and there is a chance that you could have that leaving group reforming a covalent bond with the carbocation. But nonetheless, what we do form in that first step is a tertiary carbocation and the iodide. So this tertiary carbocation is now open to both nucleophilic attack or a proton transfer. And at room temperature, ambient temperature, we would expect that ethanol will undergo a nucleophilic attack onto this carbocation. So we have ethanol. Draw our curved arrow representing that nucleophilic attack. And so the resulting structure is the following. And the formal charge now will be on the oxygen center, +1. So in a final step, because we still have a charged species, we will have a proton transfer. And so another molecule of ethanol, again, high concentration. It is the solvent. This is an example of the solvolysis reaction. Oh, keep the colors the same. And so we'll form our final compound, final product, the ether. And as a side product, we have the iodide. You don't need to redraw the iodide. You show it once here, but we will show the protonated alcohol. And so this represents the SN1 mechanism. And again, it's the predominant mechanism when you have a solvolysis reaction at room or ambient temperatures. Now, if we were to carry out this same reaction at elevated temperatures, we would observe the E1 product, which is the formation of an alkene. So we'll show that on the next slide. So again, with tertiary alkyl iodide, and the first step in our mechanism is loss of a leaving group. That will generate our tertiary carbocation. And now ethanol will act as a weak base in the formation of the elimination product. So ethanol is our weak base. I'll show the hydrogen for this particular beta position. And so the resulting alkene is shown. So what I've shown here is the favored product. This will be the major alkene that's formed via the E1 process. It is possible that you could form the least highly substituted alkene in this example, which we would refer to as the Hofmann product. For that to form, we would have to have a proton transfer occurring from one of these two methyl groups. And so we can show that as a possibility. So if I specifically show this particular beta hydrogen, and again, a molecule of ethanol, we would have a proton transfer occurring from this particular beta position. And so that's going to form your protonated alcohol. So I won't redraw that out again, but you'll form the protonated alcohol, but now you'll have a different regioisomer. Okay, so you can see we have generated a disubstituted alkene. It's a constitutional isomer of the other alkene, but because it's less highly substituted, it will be less stable. So the major product in this E1 reaction will be the Zatev product. Now, this is one way in which we can form alkenes, but of course, we'll also form the SN1 product in this particular example because we don't really have much control over that molecule of alcohol attacking the carbocation. So yes, we can increase the probability and favor the formation of alkenes in this reaction by heating up our reaction mixture, but we can't exclude or prevent the formation of an SN1 product. There are better ways to form these alkenes, and the best way to do that is to choose a better base. So ethanol being a weak base opens up for this non-selectivity in a sense, or this large ranging product distribution. But if we choose a stronger base, then we can avoid the formation of the substitution product in this particular example. So that's what we'll look at on the next slide. So if we use sodium ethoxide now instead of ethanol, this is a much stronger base. This is the active species, is the ethoxide ion. So this is a strong base, strong nucleophile, but in the presence of a tertiary alkyl halide, SN2 is not likely, it's not observed. And so the preference would be for the E2 mechanism. And so similarly, we will see a preference for the more stable alkene in the formation of this compound. But in this example, we may also form the Hofmann product. So this is the Zatev, this is the trisubstituted alkene. We could have deprotonation from the other beta position. So I'll show this hydrogen. We could have deprotonation from this position, although this will be a minor product. So we can have different regioisomers associated with this reaction, but the major product will be the trisubstituted alkene. And again, we don't see any cis-trans or EZ isomerization with either of these species due to the nature of the substitution. We have identical methyl groups off one of the carbons and two hydrogens off this particular carbon. So again, this is your E2 mechanism. So the point of showing you this last example is just to show you that, yes, you can get an elimination product via a tertiary system with ethanol and raising the heat of that reaction, but you can save the energy that you use to heat up that reaction by just choosing a better base, a stronger base. So sodium ethoxide, sodium methoxide, sodium hydroxide, they would all give you the same major product, this particular E2 product. So if you have any questions about these particular examples or how you decide whether or not a reaction is going to proceed via a substitution or elimination mechanism, please let me know by email, or we can set up a Zoom appointment. Thank you.